So what we have to do, we said last time, we have to do the thing that Xin Yang told Nambu, that he was a moron because he couldn't understand that something is either is or it is not, basically, right? An elementary aspect of logic. Okay, why we said that? Because this propagator is not, I shouldn't have erased it, but I did. I'm not going to write it again. It's not well behaved. We want to have a well behaved propagator. So in other words, I want to have a massive gauge boson that behaves like a massless gauge boson. So I have to find a trick to give it a mass. Now, of course, you all know what the trick is, right? It's called the Higgs mechanism. They're making big fuss about something that has already been seen, or so it seems. When you read in newspapers or maybe a popular thing, you will say that Higgs was found. This is still not clear. We found something that very much looks like Higgs. And we will struggle a lot to make sure that this is the Higgs boson, the celebrated Higgs boson. And maybe really it's worth making a drama. It took 60 years to find this bloody guy, where Lederman called goddamn particle. He couldn't stand it. Writing his popular book, Lederman, a great experimentalist, one of the fathers of parity violation, couldn't stand it. And the editor doesn't let him put goddamn, so it becomes God's particle. So the world is in awe of this God's particle. Well, there is something special about it, as we will see. It's not just an elementary particle. This guy is responsible for the mass of other elementary particles, and his own. Not yours or mine. We don't give a damn, really. But then it's okay, because we are classical, as you know. So what I have to teach, it's what goes by the name of spontaneous symmetry breaking, and then of course there are daily examples. You give me some examples that you know of when the symmetry is spontaneously broken, what it means. So let me just immediately define it and then ask for an example. I mean that actually the theory is invariant. That's what I want. I want to have an invariant Lagrangian, but at the end the end result is not, because the ground state is not invariant. So what examples do you know? You can think of. You know Salam's example.
Like the Mexican hat? Or what do you mean?
No, that's already a sophisticated thing. That's what I'm going to do. I will pretend that you don't know the Mexican hat. Okay, I'm supposed to teach you that. Now, if you know it so much, the better. But sort of either daily life or some example from physics.
But there are some examples in condensed matter physics.
Even before that, something even more trivial. Yes, there could be, but something more trivial. For example, take a rod. If it's somewhat elastic, and push it, there is an azimuthal symmetry, but you will see it will bend. Once it bends, there is no more symmetry, agree? See a rod which bended, and you will say, no, there is a special direction. So there are trivial examples we could see, but there is a nice example of Salam. The round table. You go to the round table, you sit at the round table, and there will be a glass on your left and your right. You have a complete symmetry between left and right. And normally you don't know, unless there is a well-defined convention. Usually it's not. Then you need some VIP to choose the... So for example, if you went for dinner with Salam, you wouldn't start doing it before he sits down. He was really an emperor here. He was a great physicist, but more than that. In the 80s, I used to come to the summer schools. I remember even David Gross and other people who would be Nobel Prize winner. You know, there was something special, and you would wait for Salam, who would break the symmetry, okay? You have spontaneous symmetry breaking. So one person takes it on the left, everybody else will follow, right? Spontaneous symmetry break. I'll start with the simplest possible example, which is not physical. Before the hat. Already or SSB. The hat is already a little sophisticated, which is a beautiful physical example of a continuous symmetry. But I'll start at the simplest possible Lagrangian and the simplest symmetry you can imagine. Which in the end may even have some physical implication as as I hope you would appreciate. So imagine that I take a real scalar field, and I take a discrete symmetry, which is E2, phi going to minus phi. It can't be simpler than that. Right? Now, if you don't like this strange, stupid symmetry, you can think of a discrete symmetry, for example, left going to right. Or particle going to antiparticle, it can be charge conjugation. Or CP, I don't know. So we could even imagine giving it a physical interpretation. At this point, this is a toy example in which I want to illustrate the phenomenon. And it's really tried to catch the essence in this example. Almost everything, almost, is here. Even thought of a Higgs-like particle, strangely enough. Although it has nothing to do with Higgs. So how does Lagrangian look like? Well, there is a kinetic energy, agree. I have to propagate the guy. And there is a potential energy. Now my dilemma is how to write the potential. So let me do another simple thing. Already taking a simple trivial example, so I'll take the simplest potential I can. So V of phi, I'll take to be 1/2. I'll give it a mass. And I'll give it interaction. Mass is so trivial, right? I need a real theory that imitates the other interactions in nature. And so the next one I can write phi to the 4th, right? Which has a dimensionless coupling, by the way. And I stop here. Imagine that this is the whole, you can think about it that I'm interested in the small values of the field, so I'm going to do a perturbation theory. Anyway, all I want to do always is a perturbation theory in small coupling, small values of the field, because I'm dumb. I don't know how to solve well, maybe not completely, but by and large, and we all. So there is also something that you will learn. This is how you have to start. You can't write higher order terms. They may appear later through loops, but you can't write them down. The theory wouldn't be renormalizable. You will get infinities. I'll comment on that. So what happens, I can plot this, this potential, right? And how it looks like, well, obviously, it's a bit steeper than a parabola. It's going to look like this, right? At 0, it is 0, and it grows. And it grows pretty fast. Well, if lambda is very small, then it will grow. Depends a bit on the value of lambda. I have tacitly assumed something here when I drew it.
Mass is real.
Sorry?
Mass is real.
I have assumed that mass is real, right? M squared. So in other words, I took M squared being positive. Okay. It's important to say that. What else did I assume? I've assumed that lambda is positive. And we really have to pause and think about these two assumptions that I made. Okay? So let's start with the second one. How firm is it? Did I have to make it? Is there any way I can avoid it? Okay? You see, I don't like what I've drawn because I want to have a situation in which the symmetry is broken finally. But here it's not broken. This is asymmetric. The ground state is completely symmetric, right? The symmetry between going from here to here, phi going to minus phi, is manifestly preserved by my ground state. Can I change this? Can I take negative lambda? I can't. Because the potential would be even bounded, okay? That would be a disaster, okay? You and I don't want to live, on a cliff, okay? Which there's no friction, okay? So this is a must. This is what is called boundedness. And it's sacred. Wherever potential you always do, you will sometimes have 2, 3, 75 fields. You got to make sure, it may be complicated, that it's bounded from below. Okay. Now, why did I take this? The reason I took this, because From that Lagrangian, I can rewrite the Lagrangian by partial integration like this. Plus interaction, you agree? I don't have to do this step, right? I've just integrated partially and drop the total derivative. That's one thing interesting that maybe at the end of the course I may need to tell you. It has to do with something called strong CP violation. Remind me that we always drop surface terms. But sometimes we cannot, okay? Here we can, there is no problem, okay? I have my field. I will assume the field is well behaved, goes quickly to infinity, so I'm dropping a surface term as usual, okay? But I'm just sort of wetting your sort of imagination. So from here I will get, if I write that phi is, if I Fourier integrate, right? What will I get? Either I write box plus m squared equal phi 0, or from here I will get that p squared is equal m squared. This is the celebrated Einstein relation, which says that E squared is p squared plus m squared. M squared has to be manifestly positive. There are no tachyons, okay? The physics of tachyon doesn't make sense, okay? And probabilities are not conserved. There is, if you and I know, so if anyway happens that you hear as in 2012, you were too little probably to know. There was an experiment in Gran Sasso that claimed that neutrinos go faster than light. Don't take them seriously. Sadly enough, a number of distinguished physicists were claiming that that's sort of okay. I'm a little proud of that. I was giving a public talk somewhere, and you know, after the public talk, you want to be asked about your own work, but people wanted to know about this extraordinary thing. And I'm sort of proud that I said this is nonsense, you know. Don't ask me, but if you ask me, okay. Nothing travels faster than light, please. Okay, I'm going to stick to good old Einstein theory of relativity. The reason is because it's well tested, not because of my prejudice. So, everything tells you that m squared should be positive. But the thing that characterized Nambu, when you Nambu was Soto or Nambu, I'm not sure how to, was a sense of courage. He would sort of try crazy things, okay? What often happens with great physicists, they try things without knowing why they are trying them. But they don't give up and know how to pursue it. So I'm going to give up on this, although it seems crazy. Okay, this I want you to appreciate. There is something dramatic happening, okay? You and I wouldn't have thought of that. Okay, I wouldn't have thought of that. Maybe you would have. But I wouldn't have done this. I would have kept on working with m squared positive. I'm afraid. So let me try. Remember, this thing, of course, m squared has to be real. There is no way I can take it imaginary. Phi is real, Lagrangian has to be real. So I'm going to write m squared is minus mu squared, just to emphasize that. And then let me rewrite the potential in the following manner. Maybe just, I'll write it like this. Lambda over 4, phi squared, minus v squared, everything squared. I just rewritten a little bit that 5. Actually, it's maybe, let me call this 5. All right. What is this? It's lambda over 4, phi to the 4th. That's what I had here. Minus lambda over 2, v squared, phi squared, plus lambda over 4, v to the 4th. So notice that v is v prime plus a constant that I added. Who cares about the constant, right? That's the first thing we are taught when we are little. What Lagrange teaches you. You can add a constant to your Lagrange and nothing changes, right? The reason is that the equations are correct. That just as the ground state, but you and I don't care about the ground state, right? We don't care about the vacuum. What we do, we measure the energy above the vacuum, correct? Well, I have to wet your mouth, wet your imagination from time to time. Not correct always. There is one force that knows even about the vacuum. It's crazy, that force. And that's Einstein's fault. It's gravity. So actually gravity knows, but you and I are not doing gravity because gravity doesn't matter, although matter gravitates. Gravity doesn't matter in the world in which we live now. And by the way, what gravity taught us, that actually this constant, the potential looks basically like this, as if the constant is zero. It's called the cosmological constant. And it's basically zero. It's so tiny, you can just think it's zero in the beginning. And notice what I've done here, I called mu square, or m square, lambda over 2, no, lambda v square. Am I right? Correct? So you see, V is the scale. You agree, I can do this, okay? It's the same Lagrangian, okay? It's just easier to see it because once you made it positive, you immediately say what the ground state is and so on. So this is the mass scale of the theory. The only scale. So everything that I get, you see, if this is supposed to work, everything will have to be proportional, all the masses to V. So you can anticipate here the beauty of what will later be known called the Higgs mechanism. That will be a complicated extension of what we are doing here. There will be a gauge structure, a group structure, whatnot. But at the end, you and I know that whoever gets a mass, whether it's some quark or a W boson, their mass will have to be proportional to that V. Okay? Already we can see that there is something profound if it works immediately here. Now, how can it work? Because I have a tachyon. I took this minus v square, I have a tachyon. Well, what we do here, I can erase this. This picture has to be changed. So what is the ground state of this potential? We have a fancy language for the ground state of vacuum. We call it a vacuum manifold. A vacuum manifold is all set of states, call it phi 0, so that V is at its minimum. Vacuum manifold. It's not so important for perturbative theory as we do, but it's actually extremely interesting to have this picture of vacuum manifold. It's important when we talk about something that is called topological defects. I don't know if you've ever heard of them, domain walls, strings, magnetic monopoles, and so on. Okay, just again, the words en passant, don't worry if they mean nothing. They may eventually mean. I will use from time to time this fancy language, just to emphasize. So what is the vacuum manifold here?
Plus or minus V.
So it's V squared equal mu square over lambda. Sorry, I'm sorry, it's plus or minus V. It's enough to say this. Or I could, why don't I write nicer? I call it phi 0. Phi 0 is plus or minus V. There are only 2 points. So I can draw this immediately. The minimum is 0, so it has to be like this. No. What am I saying?
It has to be maximum.
Is it a minimum or a maximum?
Maximum.
It's a maximum, because the second derivative is negative. I'm glad you are awake. So I can always pretend that I'm making gross statements on purpose, so that I see that you guys make a mistake. It's a good trick when I make a mistake. So it has to go like this. But it has to come up because lambda is positive. So even without doing anything, even without taking any derivatives, I know it would look like this. And I know that these 2 points are we just said, because you told me. And I trust you, and minus V. But you see what I told you. I'm going on. Although it's crazy. Why am I going on? Because what I want to do really, I don't care to live in all of this parameter space or the field value space. What I'm interested in is a perturbation theory when I move a little, you know, I quantize my field and I have my harmonic oscillators, and they are sort of describing the motion around the ground state. Okay, I don't want to jump all the way to the moon. I'm describing a theory what happens when I'm a little bit above the ground. Okay, I've come to the table and I want to jump. So that means that I'm describing my quantum system is going to live here. So maybe it's not that crazy. Yes, please.
Shouldn't be like shifted on.
Sorry?
Shouldn't the gravity be shifted on?
Oh. I can again pretend that I did it on purpose. So it looks like this, you are telling me. I mean, by adding the constant, I only shifted the ground state. And crazy enough, graviton cares, we said, but you and I don't care about the graviton. So I want to live here. Actually, it doesn't matter for what I said, the picture. I've drawn the picture. I added the constant, but in the end I didn't add the constant. It's irrelevant where I put it. I could have drawn it there and I told you that the constant, to answer that, I'll just change the constant. Anyway, if I decided I want to live here, you see, what was the meaning of a tachyon of the thing being grown? My field phi cannot be a physical field, because this will be the ground state, apparently. But I can't live here. This is a local maximum. This is the tachyonic nature of the phi that tells me I can't live here. Anyway, it's stupid even to think that there would be a problem. I can't live here. I would fall there. We have what is called a spontaneous breakdown of, of discrete symmetry. Imagine a left-right symmetric world of two valleys, a big, if you wish, ball on the top of the hill without friction. It's completely symmetric, the world, right? But it will fall down either left or right. And if you come the day after, you will say there is no symmetry whatsoever. So you and I, either we live here or we live here, because we want to stay stably near the ground state. We don't want to live dangerously on the top of the hill. We couldn't. We have a classical disaster, right? Something that is immediate catastrophe. It tells me simply, you see, what the fields that I will be using when I talk about the field, whether it's an electromagnetic field or the electron field, is by definition that sort of kind of wave function, classical field, that describes the motion near the ground state. And that's not phi. Phi describes the motion around here. In other words, let's decide, where do you want to live? It's okay if I take this? We can call this Goran's vacuum, okay? Physics should not depend. There is a complete symmetry. So if Hassan disagrees with me, he says, no, I want to live in this vacuum, I guarantee you that everything will be, if you wish, all the physical quantities will be independent of that assumption. So in other words, the field that describes physics is H. That's the field that tells me what is happening around my ground state. I could almost at this point give it a name and call it a Higgs field. This is basically what will become a Higgs field in a very complicated situation that you and I will be dealing. Actually, it should be probably called Higgs-Weinberg. Higgs-Weinberg-Salam, but it's really Weinberg who specifically wrote the Higgs field for the standard model, the celebrated doublet, okay? I've been trying to call it Higgs-Weinberg. It's not catching up. It's a very strange thing because Higgs gave a seed idea, and normally you celebrate not just the people with seed idea, but the people who have the actual theory, which is Weinberg. Actually, I had a long correspondence with Weinberg when Higgs was found, and he sort of, you could see that he would like it to be called Higgs-Weinberg, but he feels that he shouldn't. It's not up to him to say He got a lot of credit very quickly, and then now doesn't get enough credit, strangely enough. Not in the proper sense. So, most of the time I call it a Higgs field. And I'll try to remember that it's Higgs Weiber to be later on with that. This, of course, precedes Higgs. Why is it so important that I have to rewrite the Lagrangian as a function of this guy? I want you to stop me at any point I make. You may know these things. Even if you know them, you may not know them in the manner that I want you to know it. So if there is any confusion, any question on your mind, please ask. So this really, I got to rewrite as v plus h squared minus v squared, everything squared, which is lambda over 4. I got 2vh plus h squared, everything squared. Correct? What do I get? I will have lambda over 4, h to the 4th. Let me start with this piece. That, of course, is not surprising. I had an interaction. It's going to stay. I just shifted my field a little bit. Then what next? I have a cubic term, which is lambda v h cubed. This is very important. And then I have a term which is quadratic. 4 will cancel, which I'm going to write like this, lambda over 2. No, I'm going to write like this, 1 over 2, 2 lambda v squared, h squared. This is even more important. Now, why? What I see here, that H field actually is not a tachyon. In other words, the physical field, two things I say, that it's a perfectly well-defined field whose mass is 2 lambda v squared, and it's manifestly positive. It's amazing what happens sometimes when you don't have fear. Of course, you will see when you do your PhD, you often get ideas. You know, my graduate student come to me the way I will go to my advisor with discoveries. And 99.99% you are wrong. And the advisor points out, occasionally a miracle can happen like here. Which is telling you, you know, this talking about the axion doesn't make sense for you and me to speak about the physicality of a particle before we know the ground state. And of course, the ground state in which you and I live, I told you, I think I told you on Monday when I started out, is such, for example, will the photon have, how to say it? Let me put it before I ask it. What I should have said, the way we say it that the value of the field phi in the 0 is non-zero. This we call the vacuum expectation value. We call it vacuum expectation value because this classical value phi 0 that I wrote actually is a vacuum expectation value. It's the value of the quantum field in the vacuum. Okay, at the moment the name is not so crucial. Okay, so we say that our scalar field has a vacuum expectation value. It has a value in the ground state which is not zero. Notice what happened by that token. Okay, immediately. The physical field that corresponds to it, first, has a regular mass. Second, manifestly shows you that the symmetry is broken. If I write the Lagrangian as a function of h, there is no symmetry whatsoever. There is no symmetry h going to minus h. But if I don't want to do it, then I want to leave in my Lagrangian because I just want to, sometimes you want to do a calculation without physically understanding what is going on. Then you can say, I can as well work with the other Lagrangian as long as I remember how to interpret it. In this particular form, it has a symmetry. So, for example, you notice that you have always assumed that the electron has a zero vacuum expectation value. You always assume that. and that the photon has a zero vacuum expectation value? You always said that in the Dirac equation, the psi describes the motion around the vacuum. Could psi have a vacuum expectation value? What would happen? An electron or a photon. So we often say, you see this phi 0, let me put it this way, we write like this. A vacuum expectation value. I may be using this just because it's used, or I may be using this, or I'll just say it in the word. So can I have a mu 0, non-zero? And this is manifestly non-zero, right? Because this is plus or minus square root of mu square over lambda, which I call V. What would happen if photon had a vacuum expectation value? Some symmetry would be broken. Would be broken Lorentz symmetry. And depends which one. If it's a time component, you would break Booth, but you could still have rotational symmetry. If I take the wave in the direction of a 3, I will break even rotational symmetry. Now I will assume, for the sake of the next, us simplifying our life, that Lorentz symmetry is good. As I told you, the charge is preserved and the Lorentz symmetry good. There are some sacred symmetries. I'm tacitly assuming one of them is Lorentz symmetry. So I can't have that. And this is why you assume that, and it's consistent. If you look at your Lagrangian, you will see it's consistent. There is nothing inconsistent. For example, here the assumption that phi is 0 is wrong. It's simply not true. When I draw the picture for my potential, I don't even have to compute. I see that it's wrong. This is why we have introduced, why they have both Goldstone and Higgs later on. This collective is a funny way to speak. Why these geniuses have introduced the scalar field, and why many people didn't like that. Many people said this cannot be true because there are no elementary scalar fields. A lousy thinking. There's also no river before you see it for the first time. Or the sea if you come from the desert. Or the desert if you come from the sea like me. That was a lousy argument. I hated it. I must say I'm really glad because, when I studied my PhD school, I had to decide whether I'm going to stick to the Higgs mechanism or I'm going to look at alternatives. Even the father of this physical interpretation, Weinberg, immediately looked for the alternatives. They're called technicolor, complicated, to me meaningless games, saying that there is something unnatural, two things they would always say. Even himself, I don't understand. He's sort of a master that was an inspiration to me. They would say that, well, I'm inventing a scalar particle, but there are no scalar particles. Well, so what? Second thing you will often hear, that the problem with this scalar field, that you cannot say anything about its mass. You cannot make any prediction about the mass. Now, how could you ever think about it? What would that mean that you predict the mass? How can you predict the basic parameter of your theory? That you cannot do. What you can do is to correlate your mass to some other physical quantity. From today onwards, what we are after, you and I, when we claim that we have a theory of mass, this means that I correlate the mass to physical processes that can be measured in a machine like the one near Geneva. Okay, that's what I mean. I can't predict the mass because that's my input, but I can correlate to something else. Okay, remember that. Because you will read, you may have even read or heard, that you can predict the W boson mass in the standard model. That's a lousy statement. I tell you what it means, actually. It's not predicting it. You relate it to the Fermi scattering because Fermi scattering has been measured. And notice, however, that they are all wrong, including Weinberg himself when he said that, okay? This is what bugs me. I am actually relating the mass of the particle to the scattering process. I just didn't measure it. The same parameters lambda V enter into the... There is a profound correlation of the future Higgs mechanism already in this trivial example. Find the particle and measure how it scatters on itself. Take two of those H's and see what happens when you scatter them. You'll be measuring alpha. Try to measure the H cube, right? 2 going into 1 and so on. And you'll be measuring independently again lambda and V. So actually, by all the criteria, this theory satisfies what we are asking from a theory of mass, to correlate the mass to the physical processes like scattering. Second, it's extremely simple and very predictive. And that should be measure of beauty of a theory. This awful thing that entered in our field to measure the beauty by the baroque complexity of the statements you make is a totally unphysical way of looking at nature. Great theories are those that are simple, predictive, that you and I can go and test. That's what physics is all about. The way it starts with Galileo and Newton, and not with Democritus. Okay, that's not good physics for us. I want you to remember. Okay, I'm going to insist on that. So I told you I'm really glad that I never work on the alternatives. And I won a lot of money already, because we now believe that Higgs is there. We physicists, well, some of us, I'm a compulsive better in physics, so we bet. And it gives you fun. You see, if you bet a lot of money, you're going to work with more, believing in that. I won a lot of bets on the Higgs, okay? There are always people who didn't believe in that. Any question here? Last night, late in the night, I was talking to my collaborator, friend Giyad Bali in Munich, who also teaches things like this, and we were discussing, when you teach this, I was asking him, and he was asking, do you do this, I was very much in a dilemma. The following dilemma. Whether I should wait for you to ask the question or actually tell you. I've actually cheated on you badly. Well, I didn't really cheat, but you should feel that I have cheated. For example, if you have studied quantum mechanics, and I think you have, all of you, you should have objected to me. So maybe I'm still not sure, you see, even in real time I'm not sure, okay? Let me go on and wait. I bet your imagination. You had no problem accepting that I told you I live here. Well, it's true, I drew a classical potential, so you can tell me, yeah, at the classical level, but then I said I want to describe the quantum world in which actually this is a vacuum expectation value, and I have my quantum field living here, okay? Not clear yet where Let's summarize while you are thinking. Another advice that I have for you, by the way, when you do the homework, I can't overemphasize that. And that will be the thing when you do research, okay? Well, I don't know if this advice is ever helpful. Because if you don't have it in you, maybe you won't do it. When you do the homework, or when you're doing research, and you thought something, and you wrote it down, and you just leave it there, it's okay. You've done it. But most of the time, a little discovery, whatever you do in life, is keep staring at what you've written and trying to really understand it, to look at it a little different, to think if there is another way of deriving it. If you just have a little patience, and that is reflected in homeworks, you may do what research is all about. Sometimes just by I know, of course, there are other homeworks to do and so on, okay? So whether this advice is useful to or not, I apologize if it seems trivial and obvious. So this was my potential, remember? Then I said that phi must be V plus H, because I have the vacuum manifold, which was phi 0 is plus or minus V. And I chose the point plus V. We could call it here, I don't know, H Goran. Because we could also have H Hassan, who's taking minus V. But look, what I got immediately from here, mh squared, is 2 lambda V squared. Notice it doesn't depend on the sign of V, as I expected. He should get the same mass that I get. Okay, that's very important. And the potential looks like lambda, so let me write it maybe in the usual manner, 1/2 mh squared h squared. I'll start calling this Higgs field, although it's too early. Well, it's terrible this with names. The first person to notice the existence of the Higgs field. It's sort of funny that typically, fortunately not always, most of the credit goes to the second person, not to the first person. Usually the first person kind of gets forgotten because the work is too original. Okay. Not all. This was actually noticed by Goldstone 6 years before Higgs. By the way, Higgs even didn't notice that he had a Higgs boson. He sends a paper to the journal. He was too bloody lazy or whatever, or maybe excited about what he's done, that he didn't even check that there was this Higgs particle. The referee apparently, well, sorry, not apparently, no, because he says it was Nambu. And Nambu, instead of writing the paper on his own, tells him, you know, just think of the physical consequences. He takes the paper back, works it out, and finds out that there is the physical consequence, the existence of the Higgs boson. Okay. But he was noticed before by Goldstone that maybe Nambu didn't know, maybe Nambu knew. It's too late to know now. Then I get the term lambda VH cubed. And I get the term which is lambda over 4 h to the 4th. The discrete symmetry Z2D is broken. H, there is no symmetry, H goes to minus H. It's broken, but it's broken spontaneously by the ground state. Okay, this is what make it stop. Let me. Now I have a dilemma whether to move to the physical situation of a continuous symmetry. As I said, and I said it a little quickly, let's say, in the standard model, of course, there is no discrete symmetry that is spontaneously broken, so it says who cares, but there are physical examples that people have studied. One is breaking of parity symmetry, left-right symmetry, so this discrete symmetry could be parity. Right, it's a discrete symmetry. Remember when UL, fermion, FL, goes into FR. Or it could be CP. CP is the product of C and P. And the P left goes to right. Under C goes into the star. So under CP we'll study it, but maybe you remember, FL goes into FL star basically. Up to the constants, the gammas, whatever, right? You must have talked about CP and Kobayashi Maskawa, right? Yeah. Okay. So, for example, the idea that CP is broken spontaneously was studied by T.D. Lee in the early 70s, and the idea that parity is broken Spontaneous is the work. It's actually my first paper with work of Mohapatra and myself. And it will be important to, so remember this example, I will try to tell you that it is maybe fundamental, but it has to do very much with neutrino physics. And the standard model is all about parity and the way it is broken. It will turn out as a boomerang, okay? Trying to avoid the issue of left-right symmetry, it will hit us back. Because that's what the fathers of the standard model. Remember what I said on Wednesday? The world is just asymmetric. Says T.D. Lee, Young, Marshak, Sudarshan, Gleshow, Weinberg, Salam, all these guys, they tell you. And if you ask them, why is the world like that? They shut up and eat your spinach, you know, the way you tell as a kid. That's not a question you should ask. Okay, but keep in mind, these are the people that predicted the neutrino to be massless, so we will have to come back to this. So this may be relevant for us. But normally I stop here unless you ask me. And I go immediately to the more interesting case of a continuous symmetry, which is called the Nambu-Goldstone model. I'll still wait maybe for a minute or two because we may have some other questions. Telling you that I did cheat solo. Well, let me ask you. Well, I can't help it, so I'm going to ask you. Okay? If you read one of the chapters in Feynman's first volume, I think it's 19 on the principle of least action. It says he had a great teacher in high school. What's great about his teacher, he knew when to stop. He says, I don't know when to stop, says Feynman. Just like Feynman. And maybe, okay, he was a great lecturer. I still feel like bugging you a little bit. What would happen in quantum mechanics here? I mean, you studied quantum mechanics.
Yeah.
Is this true, what I said, that you live here in quantum mechanics?
No, you can go to the other side. Like, so
No, because you tunneled. But you didn't mind that I told you that I live here. So this is the obvious thing. If you speak with enough authority, and maybe if you have enough grade, I don't know, but even if I was younger, I think, and I spoke with authority, you would believe in me. This is not true in quantum mechanics. This is one of the first calculations you do. You know that the ground state is symmetric. You can compute the ground state. And the reason it's symmetric because tunneling is the first beautiful consequence on quantum mechanics, right? You don't have to jump over the crazy barrier. What happens is that in the field theory you have infinitely many degrees of freedom, not just 1 degree of freedom. So if you remember the tunneling amplitude, I don't know, WKB. You remember what it was proportional to? You remember that it was exponential? And when you had to tunnel from points A to B, it will be an integral from A to B. Of course, it's now in the x coordinate, right? There is just one coordinate. What we will get here is a square root of E for zero energy. There's also energy in the game, but the energy is zero. It's exponentially suppressed, dx. So for example, if you take a constant barrier, I can sort of do this, right? This would be the square root of E0, let's call it, times B minus A minus B, whatever. So it depends on the barrier, of course. It's not surprising. The bigger the barrier, the harder is the tunnel. Okay, there is, even quantum mechanics knows about the problem of the size. You know, infinitely large barrier, you're not going to tunnel through. It also depends on the distance. If you're far away, it's going to take you more time to distance. But now imagine that you have infinitely many degrees of freedom associated with your field. It's not surprising that the tunneling doesn't take place. I've assumed tacitly one of the most profound results of field theory, and there is a beautiful, the idea to study it was Okun, Kobzarev, maybe Zeldovich. But then he was taken more seriously by Coleman, who developed the theory, and it's called the fate of the false vacuum. So what he realizes, okay, just like in all the systems where they tunnel, you know, what heat the water, and you will see what happens. You got to produce a bubble that then grows. So the tunneling takes place by producing the bubble. So what he did, to understand what is going on, he did the following situation. Imagine a potential which actually looks like this. To understand how tunneling takes place, right, I have to imagine a situation in which I know that I will end up here before or later. Okay, and imagine that you and I got caught here, and now we are wondering what's going to happen to us. So, and he solved the problem analytically for small if you wish, for the small breakdown of degeneracy, yeah, right? You had two degenerate vacua which are now broken a little bit. So this delta V over V, call it epsilon, is much less than 1. What he understood, you know what happens? You create a bubble. So you are in the, is that intuitively clear? I'm not going to do the theory of vacuum tunneling, but now because I said it, I will just say a few words. What happens is, you know, it's just when you are heating water, there will be a bubble. It's going to form because it's energetically favorable. You create the bubble. So I get a bubble. This is false vacuum. The one which is there at minus V. And this is true vacuum, plus V. So I think immediately, of course, this should grow immediately, right? It seems obvious. You would naively, if you don't think a little bit about that, you would say, oh, but why does it just grow exponentially? Okay, here there is less energy, so it wants to grow. I want to minimize energy. Well, remember that what you have to do, this bubble has a wall, because what happens is, there is, of course, less energy here, but you have to change your field from plus V to minus V. There was minus V, right? So there are two things in the Hamiltonian that is associated with this. If you wrote the Hamiltonian, and we are writing a static Hamiltonian, right? There will be 1/2. Imagine this coordinate to be r. There will be d phi over dr squared coming from the, we'll call it z, whatever you want to do it, coming from here. You agree? I'm just looking at the static case. Plus, this will be the potential. So obviously, I'm gaining by being here, but I have to do something highly non-trivial. I have to change field from minus V to plus V. It's going to cost me energy. You agree? There is a surface tension, if you wish. This wall is there because you have to go from the value of the field minus V to plus V. So what happens? I don't want to argue with details, okay? Because it's sort of involved, but you can imagine that what's going to happen. There will be. If you look at the energy of the bubble, you will find out that there is minus, let's call it epsilon r cubed, the volume piece. I'm taking pi equal 3 equal 1, plus there will be a surface price you are paying because it costs you energy to do that, which is some surface tension times r squared. Or even here, sorry, energy. This is just delta V. Sorry. It's not a dimensionless number. This here is of order, well, it's delta V. No, sorry, it's not of the order. I can't specify. It's some delta V here. Is this clear? This wants the bubble to grow because I want to minimize the energy. But this wants the bubble to shrink.
It's kind of like the liquid drop model of nuclei.
Size. And obviously there is a critical size of the bubble. So you have to wait till it grows, and then it will start nucleating. And then it will happen. So, and this you can see, this is the order. If you put the dimensions, you will get V cubed. The only scale here is this V. It doesn't matter, these are details, okay? The crucial thing is there's a critical size of the bubble, so the tunneling is very hard to achieve. Where he goes on, so this was the WKB. In quantum mechanics, what he finds out is basically that gamma field theory tunneling. This is a Coleman formula. For the thin wall, it's called a thin wall approximation. The wall is thin, everything is small, delta V small compared to V. You get something which is proportionally exponentially suppressed as 1 over epsilon, if you wish. There are other quantities to enter. Epsilon I took as a dimensionless quantity. Delta V over V. There are many factors here. And actually there's a power even. It's really tremendously suppressed. So when epsilon goes to 0, the tunneling exponentially vanishes, okay? You can't tunnel in field theory because you have to bring infinitely many degrees of freedom, as if you're taking the WKB approximation and then integrate it over a long video, one dimension, infinitely many degrees of freedom. You get an infinity that suppresses you there exponentially. This is very important. This is why there is spontaneous symmetry breaking. We can talk about in field theory. You know, once I establish that, I can relax. I didn't pretend that you've learned anything here. I just hope that you got a sense of picture of what is going on. Okay. This part is, if any of you want to read it, at any point later we can discuss about that.
Is there any paper of Coleman describing this?
Yes. This is the celebrated fate of the fault vacuum. There is more than one paper. Actually, the situation turns out to be more non-trivial in the presence of gravity. So there is a nice paper. This is Coleman, and Coleman de Lucha wrote the paper, what happens if you do not ignore gravity. And the reason that you want to do that, because sometimes you may be at the scale in which gravity, you aim at study your system, for example, near the grand unified scale. You heard of the grand unified scale being very large.
Yeah.
You heard that? Near there, near the Planck scale. Well, it may mean nothing at this point, okay? But towards the end of the course, some of the buzzwords I'm using will become real. Fate of the false vacuum, Coleman. Beautiful work. I'll mention along some of the sort of most beautiful papers that I will find that describe great physics, okay? Like the Dirac paper on monopoles. I'll have to mention it as I go along. But when it comes to field theory, there are two papers that stand out. One is the fate of the false vacuum by Coleman, and the second is the Coleman-Weinberg famous effective potential. It's not Weinberg, the standard model. Eric Weinberg is student of that era. But I'm running ahead of myself. First things first. So I presume that you learned spontaneous symmetry breaking in 1 hour and in 10 minutes. And I'm worried that maybe you didn't. Or maybe I'm worried for nothing. Maybe you actually learned it. And I should forget my worries and simply go on. Just do it, said Nike. Okay. If this is clear, we have to move to a continuous symmetry. And an idea of Nambu described by two beautiful papers by Goldstone in 1961. The actual things that I'm teaching are these two papers of Goldstone. So if I want a continuous symmetry, can I take a real scalar field? Continuous means that let me be precise, that there is a continuous, little by little change. And that requires a complex field, you agree? In principle, you know, what I'm doing, I'm taking a U1 symmetry. And remember that there was a charge here. It has to do with what charge you're carrying. Really, what I would write here would be Q5. But I can always normalize the Q5 being 1. That's the only field I have at the moment. You agree?
Well, if you take more than one real scalar field and take point symmetry.
Sorry?
If you take more than one real field and take point symmetry on it.
Well, more than one real field is a complex field. Two real fields are equivalent to a complex field. It's just, that's what complex numbers are. At the end, all the numbers are real. It's an imaginary thing that, sorry, I'm kidding. It's useful to think of them, but the complex number is x plus iy. X and y are really real. So sure, we'll see it. We'll see it in the language that you like. So I'm going to take Q5 equal 1. You agree? Does it make sense to introduce a charge when I have the only field? That means that phi has to be complex. So I would write my potential, my Lagrangian, d mu phi, d mu phi star, minus v of phi. And here is the embarrassing part. That's what I told you. It's that trivial. Some people, you know, Valery Rubakov, well-known Russian physicist, often comes to visit us. He's a good friend of ICTP, and we often talk about that. When you were young, especially, he says he still suffers from that. Sometimes I do. But something is very easy, you think that maybe it's not important. You're doing some work, and it comes out trivial. There's this uneasiness when you're a graduate student. And very often creative things are actually trivial. Like if you look at the Dirac paper, it's really easy compared to the things you are going to be doing for your PhD, okay? It's mind-boggling really easy. And this is embarrassing when you do symmetry breaking. It's one and the same thing we are writing. This is just lambda over 4, phi squared, minus v squared squared. That's all I can write. It has to be at the absolute value, you agree, because I wanted to have a continuous symmetry. But it's basically that potential. Which seems that I'm boring you, it seems that you know this. I don't see sort of excitement of learning new, right? That's a fact. Okay. I can write, well, people like to do this when they work with complex fields, most books, because then they think that Hassan wants me to do, to write a real complex number as real numbers. Okay, sure. We can do that, and then because of the, you know, phi 1 and phi 2 are normalized normally, so we put the square root of 2 here. So in other words, if I do this, Lagrangian, my Lagrangian, let's call it Goldstone Lagrangian, Goldstone Lagrangian would be 1/2 d mu phi 1 square plus d mu phi 2 square. I now write symbolically minus v of phi. Minus this potential, and this will be just, I should have written lambda over 2 here. Lambda over 4, phi 1 square plus phi 2 square. Tell me one thing, what is the vacuum manifold here? I don't even have to, or maybe I should draw it. Maybe this is it. So we've learned this, right? We can erase it. What was that? The potential was lambda over 4 h to the 4th plus lambda h cubed plus 1/2 mh squared. Let's keep this. So let's erase this.
It was lambda b in the vector.
Yeah, maybe better to be dimensionally correct, you're saying. Good. See, it's great. I see you're very and following in spite of the hunger that creeps in around this time. This was my potential, right? V 5. Now I have phi 1 and phi 2. So this potential will look like, how will it look like? Looks something like this, right? A sombrero, a Mexican head potential. Right? There's no reason to do any derivatives or not. Do you agree? I don't know if you agree. Well, it doesn't matter, but now, why we call it a Mexican head, you know, you've seen enough movies with So really, the vacuum manifold is now what?
It's b times e to the
Phi 0 square. What is it?
b.
No, but what is it? It has a name, this vacuum manifold. Previously, there were 2 points.
Now it's
Circle. It's called a circle. This is a manifestly, well, it's not manifestly a circle. This is a circle. This is supposed to be a circle, right? You see, sometimes this is very convenient to write your field like this. But sometimes it's not. as I will come in a second. Why is it a circle? Because I have phi 0 squared is phi 1 0 squared plus phi 2 0 squared. There are 2 of them equal to v squared, right? So maybe phi 0 squared is 2v squared. This is, no. See the stupid normalization that I did. I should have called this over 2 if I want this relation, right? So this is y over 2 because I have a half in my normalization. I wanted now to imitate the others. Normally I actually put a half there and, well, it doesn't matter. You agree? Phi 1 0 squared plus phi 2 0 squared, this is called a circle. Okay. And now the point is, just as before, I could choose the point in which I live because of the symmetry. Any point is equivalent to any other point. And I chose to live in the point plus v. I will choose the point on the circle where I want to live. And they are completely symmetric. The physics should not depend. And it didn't. All what I got before, I kept it, okay? This was in my discrete case. Z2. Just to remember it. So really, what I should write by phi is 1 square root of 2. Let's call it phi bar. Is v plus h plus I don't know. How should I call it? Maybe G for Goran. Okay, I want to leave, I've chosen my point of vacuum to be V. You may choose minus V or V e to the I pi over 2 or V e to whatever. I'll convince you that physics doesn't depend on the choice of the vacuum. Okay. What will happen here? Maybe we can see it here. How does the potential look like? Well, it's better here. No, it's better here. This was the piece of the discrete part. What will I get? This will be lambda over 4 I have a half, then I have V plus H squared plus G squared minus V squared, everything squared. This is lambda over 4, 2VH plus G squared, everything squared.
H squared.
Oh, you want H squared also? Okay. See, I'm reasonable. I mean, remember, everything you told me today, I didn't quarrel at all. H squared. If you like H squared, I give. There is a set of predictions, immediate ones. Once notice, I will get the same mass term for H. Notice, H is the same. That's why I decided I can even call it Higgs later on. There is a scalar field whose mass is 2 lambda V squared. Is this guy H? I call it H. You know, anticipating that it's going to be Higgs, H for Higgs. But actually Goldstone noticed this. Goldstone wrote this. Two things he noticed, one that Nambu actually noticed before. What is the other prediction? So here also the same prediction. I, mH squared is 2 lambda V squared. And the second, what is the mg? What is mg? Sorry? Zero? Sergio says 0. Who else? We can have Paul. 0. Osama says 0. Any other takers? 0. Hassan 0. Mara? No? 0. 0. Okay. By Paul we won. The 0 won. Well, it's 0 because there is no constant term anymore. It's 0. This is the celebrated Goldstone boson.
I think you can also stand with G for Goldstone.
I think it's better for Goldstone than for Gorham, okay? This is a Goldstone. Now look at the irony. I tell you that the second person very often gets the credit. It reminds me of in 1985. I used to come in the 80s, I would lecture in the summer school. That's how I fell in love with Trieste. That's why I'm here. That's why I'm teaching you today. My whole life was transformed when I used to work in the States. In 1985, Salam invited me to give a review talk on the physics of spontaneous symmetry breaking that we would call now the physics of Goldstone bosons. And I start the talk, and about 2 minutes later, Salam enters with a familiarly looking Japanese gentleman. Okay, I have a bad memory of facial. It was terrible. The guy looked very familiar, and I'm really embarrassed because many years ago I had a dinner with that guy. And I start speaking about Goldstone bosons, and Salam is getting sort of somehow angrier and angrier. And you know, and he was a guy who would express his anger, so you know, 5-10 minutes later he sort of screams from the end all over, can you do me a favor? Can you call these particles the Nambu Goldstone bosons, you know? The Japanese gentleman blushed, okay? That was Nambu. He was a good friend of my first boss, Akita, who actually took us when I was a graduate student. I didn't recognize him. That was embarrassing. Of course, it was great for my talk because I had transparency. So every time when there was Goldstone, it was one and transparency, I would then write Nambu Goldstone bosons. Everybody would laugh. Everybody was happy. I still often call them Goldstone bosons. It's Nambu who notices that there will be a massless particle. What Goldstone does generalizes to any. Actually, he completes the proof. It's interesting with Weinberg and Salam. They will write, the three of them will write the papers. This is where, so the Weinberg and Salam became friends, as they used to say. Weinberg still repeats. Doesn't like to travel. We can't get him here. But health, some issues and so on. Doesn't like to take cross-Atlantic flight, but he's a good friend of ICTP. So it's called Goldstone boson, although Nambu discovered it. This is called the Higgs boson, although Goldstone notices. Goldstone explicitly writes that ma square is 2 lambda. Notice I got the same expression. And look, when I continue this Lagrangian, okay, what I'm going to get for H is exactly this. The potential is going to look like this, you agree? Please check. Forget G is the same Lagrangian as before. This is why the discrete set is so beautiful. The whole physics of this complicated, strange Higgs-Weinberg boson is hidden. Then there will be a term plus lambda over 4, g to the 4th, right? And there will be other terms not so important. They will interact. There will be lambda over 2, g square, h square, and there will be some other terms. Let me not write all of them, right? But you see there are terms like this and so on. The symmetry is gone. We have yet another example of spontaneous symmetry breaking that can be generalized. There is a Goldstone Theorem. I may prove it, I may not prove it, depending on the mood. I will show you an example for sure, which says every time you break a symmetry, and that means. So what it means? Well, now we should say it clearly. What it says, so it would be good to go back and introduce the charge here. This is the privilege of the blackboard. Of course, there is nothing interesting here. Q5 is equal to 5. It's really 1, the charge. But look at phi 0. Phi 0 is non-trivial, right? Q phi 0 is equal to phi 0. Right? Phi has a charge 1. But the U1 transformation is e to the iq alpha. Q is 1. Just keep it, here, just to you don't have to, okay? It tells me that when U acts on phi 0, I will not get phi 0. You see? Vacuum breaks the symmetry. If you wish, it's here. Vacuum carries charge. The breakdown of symmetry is associated with the strange thing. Vacuum should be empty. You and I live in an incredibly strange world, which is full of charge. It's not electromagnetic charge. That's not broken. There is this SU2 charge we learn. But in this example, you and I would live inside some kind of ether, which is full of charge. But you and I can't know that. Ever. We are like fish in the water. Well, fish gets an illumination, gets an epiphany when they fish it out. And unfortunately, it usually dies and gets eaten. But there is a moment of understanding when fish is out of water, that it actually lived in the water. But in order to know it, we have to get out of this ether. I don't know how to call it. So the manifestation of spontaneous symmetry breaking, that the charge does not annihilate the vacuum. So it says the following. When some charge Q acting on phi 0 is not 0, we speak of spontaneous symmetry breaking. It's obvious, because vacuum carries charge. And it's not invariant under transformation. Symmetry is broken. Okay, I like the case when the vacuum was at 0. Remember when the vacuum was at 0? Everything annihilates 0. This is a safe vacuum. There may be other vacuum which don't break symmetry. 0 is the best example, but you don't want to break 0, some symmetry. Make sure, maybe, try to have a field be 0 in the vacuum. Okay, the safest one, maybe we'll manage by some other way. So this is the idea of spontaneous symmetry breaking. What Goldstone will prove is that every time you break some symmetry spontaneously. For every charge, he finds out there will be a massless Nambu-Goldstone boson. I'll try to remember to say Nambu-Goldstone boson. But if I call it Nambu-Goldstone boson, then the Higgs boson should be called Higgs-Weinberg boson, and so on. Okay. Let me try to be consistent with what I'm saying here. Now, why did I get this Goldstone boson? You know, I wrote some formulas and I got mg equal to 0. I should have known that there would be. So really this was, yes, that's for Goran, but this was phi Goran really. If you want to see what is going on, I've written this many times. Then there is also phi Goldstone. I did this thing because Hassan wanted me to do it. Well, actually, it's not true. I normally start like this, but let's make Hassan happy. He says I can write like this also. I can write a complex number. You see, sometimes it's good to write a complex number as a collection of real numbers, as you know from real life. And sometimes it's much nicer to write it as a complex number with some absolute value in the phase. So if I write it as an absolute value in the phase, it would look like this. I live, this is my vacuum. So this is Goldstone and Goran at the same time. We've chosen, in this example, Goldstone, and I've chosen the same vacuum. Okay? And it has to be G over V, you agree? The phase must be dimensionless. Field carries a dimension, so that's V. V is a dimension of mass. I could have written it like this. You agree? And maybe with some square root of 2 or not, I don't know. Probably. Because notice then that phi Goldstone, I'm sorry, squared is V plus H squared. There is no G field. I got rid of the G field, you know, like a magician trick when you know, he takes a pigeon, becomes a handkerchief, or vice versa. It looks strange. Where the hell did G go? How can I lose degrees of freedom? Well, it's there in the kinetic energy, right? This, you know, there is no gauge freedom, but sometimes people even using this language, sort of, this will become more clear when we speak of the gauge symmetry. This is a global symmetry. But sometimes people say, oh, I'm in some kind of a different gauge. What I mean is, you see, for example, this is very, very convenient way of doing calculation because everything is linear, okay? And your kinetic energy and everything is canonical. Here you will get G in the derivatives. I'll do it next time, you understand, because d mu phi squared will carry derivatives of G. We're not going to do calculations with this, okay? But you see immediately, G is the phase of the field. And it has to be massless because in that direction that describes the circle, the system is equipotential, which should be clear from this picture. So it may not be the way I drew it. That obviously has to be there. It's kind of trivial. It costs me no energy to go along this line. And so the particle, because the mass of the particle is the measure of the energy. Remember, even you, when I'm near the maximum, then I will get minus m squared there. I will get a tachyon. When I'm near the vacuum, I got the energy that costs me plus m squared. Okay. When there is no energy to pay in this direction, I get a massless Goldstone boson. I've sort of, to some degree, I've proven the theorem. Well, in some examples, if I have 3 generators, you will see I'll get 3 Goldstone bosons, but we can do the formal proof. But the essence of the proof is here. Both physical and mathematical. Can you think of some global symmetry that could be physically interesting? Just, I'm finishing, just to see if you have some questions or not. I have a question for you. In the standard model, you know, is the gauge symmetry. Remember, SC2 cross 2 cross SC3. So this example you may say is irrelevant. Why am I bugging you with this? Well, first, to learn what is going on, it's better to start with an example which is easier to comprehend. Second, there could be, and it's interesting to think of these particles, there could be situations where global symmetry is spontaneously broken. You know of some global symmetries that seem to be exact? I would imagine that Alexei should have talked about it, but then you never know. There are certain things we never think to happen. Then when we never think to happen, we can associate conservation law with them. Charge, for example, electromagnetic charge, where we gauge that, sort of, it's an example of where there is a photon associated with that. It's not a global symmetry only, right? You agree? But some other similar thing, baryon number. We've never seen proton decay. Even lepton number. We've never seen lepton number violation. It's a desperately searched for, literally, for decades. This is the essence of modern particle physics. Because it's very strange that a global symmetry would be exact. There is nothing special about it. There is no dynamics that it associates itself with. And in the end, for example, the neutrino, people used to imagine the neutrino was massless. They were sure, standard model predicted it, and you get more symmetry. It's called, when Fermi mass goes to zero, you knew the other day, you get Charles symmetry. So people, but then it was broken. Neutrino has this tiny mass and breaks the symmetry. Isospin, almost perfect. Proton, neutron, almost the same mass, but yet it's not the same. So we are that sure, most of us. We are betting, I'm still betting on proton decay.
In favor or
I've been waiting. Sorry?
in favor or against?
No, in favor. I bet anything. The trouble is I may die before. Well, I made a bet with a young man recently, you know, that may take many years. So my daughter would have to carry on my bet in case I lose, you know. It's going to be a burden on her, but anyway, there's the... We also believe in the baryon number should be broken. In principle, it could be also spontaneously broken. We can think about that. There could be some Goldstone boson associated with that. We believe in that because there's a theory that actually predicts that proton decays. They're called grand unified theories. And many of us believe that lepton number is broken because there are theories that predict it. There is something which is called the seesaw mechanism that some of us came up with in the 70s. And according to the seesaw mechanism, neutrino would be a Majorana particle, okay? These are buzzwords, okay? But I want you, in my final minute, to know in the standard model that the way I teach you is to pave the door for the new physics at the end of the course. And since neutrino is massive, we'll have to talk about it. So there is a deep prejudice, yet not materialized. So there are, in the 80s, there were tens of experiments. Everybody in the world, as Goldhaber, the father of the idea, Maurice Goldhaber, said everybody rushed down when grand unification, you know, underground, looking for proton decay was never found. Now everybody is looking for lepton number violation. Do you know how the process is called? Alexei must have mentioned it, I can bet. Doesn't matter, I stop here. So we have examples, all I meant to say, of global symmetry that could be spontaneously broken. So it's good that they are ready, that we know the machinery, that we understand the physics of these things. Okay, although it doesn't really correspond to the standard model.
Can it happen that the left-right symmetry is preserved at higher energy, so it is spontaneously broken?
Well, that's what some of us believe, that I've invested fortune in that. My whole life was I was 5 years old when I noticed left-right symmetry in a mirror, and I was fascinated by that. And then I learned 20 years later, a little later, that actually Salam thought about it, and Salam says that maybe the world is left-right symmetric. By the way, I took it very seriously, much more seriously than he did. And I gave up on that because there was no LHC. I came back to it in recent years because of the LHC and also because of the fact that meanwhile we managed to prove in recent years that it's a self-contained theory. I'll have to tell you at the end of the, I finished this work recently. What I managed to do with my younger collaborators is to show that the theory does the same thing that Weinberg does for the charged fermions, exactly. It took me some time to convince Weinberg. That would be an example of the spontaneous symmetry breaking or discrete symmetry that I wanted to give you. There could be even CP invariance, but left-right symmetry has, of course, a more deeper meaning because of neutrino. It turns out if you believe in that, neutrino has to be massive. So this was very interesting. Because of the left-right symmetry, I started to believe that neutrino is massive in the 70s. And a lot of these people would tell me that I was wasting my time. I'm glad now that I decided to waste my time. Everybody knew then that neutrino was massive. Okay. Any last question? Well, we'll do some examples. And there are actually a number of scalars. In the case of SU2, for example, of the standard model, there will be 4 of them. But you can sort of anticipating. So usually you get more scalar when you have a bigger symmetry. I could just keep adding scalars. I don't want to do that because I'm a minimalist. So I will never add anything that I don't have to do, okay? And I really try to stick to that. So I get more scalars normally when I have larger symmetry, right? Suppose that I have SU3, then I'll have at least 3 complex scalars, right? Or maybe 8 if it is a joint representation. Suppose I take SU2, I need at least 4 of them if it's a doublet, right? A doublet, which we call phi, remember is complex. It has up and down components, or we often call it phi 1, phi 2. Both of them must be complex. I don't know. It's not this phi 1 and phi 2. You'll get 4 of them. So you can sort of have a bookkeeping of the following. There will be always one direction where the symmetry breaking takes place. You know, what we call phi Goran. You know, I will choose a certain direction, okay? So you can take a different. So, notice here that the mass, I could have done a better, by the way, this mass that I wrote, G square, okay, we'll discuss it next time. There is more, let me just answer this. There is sort of, since you wanted an answer, in a nutshell, the following would happen. There will always be a so-called Higgs boson in the direction of symmetry break. That's the guy that Goldstone noticed. Let's call it a should I call it Goldstone boson? I tried to do that, by the way. I started to call it Goldstone Higgs Weinberg, okay, and then I confused everybody because people think of it. They thought that I don't understand what the hell I'm talking about because they don't know really what was going on in the history, okay. I was fortunate, you know, I studied my PhD school at the time when many of the ideas were developing, so I'm a kind of witness of history, okay. Survived. So all of it. So you can remember it, there will be a direction of symmetry breaking. You are going to get the particle that we call the Higgs boson, whose mass will be precisely always the same expression that within this case. You will get some numbers of massless particles depending how many generators were broken. The generators are broken when they don't annihilate the vacuum. So if you have 3 directions, for example, you break SU2. Now that you ask, I can ask you, if I break SU2 down to nothing, how many Goldstone bosons I expect? Number of Goldstone bosons. So now let's say, aggregate. How many do I expect? If I break SU2 to nothing.
But it has 3 generators.
3 generators, so 3 Goldstone boson. Suppose I break SU2 down to U1. How many then? 2. I broke 2, 1 remained. U1 means that 1 remained, and so on.
The remaining one is Higgs.
The remaining one, well, there may be sometimes even an extra particle which is neither Higgs nor a Goldstone boson. Typically it won't happen in a small representation of a small group. But if you have a big group, you may get a lot of other particles which are neither Higgs nor Goldstone boson. There is no a priori rule. You know, there is a theory, let me say randomly, let me take a random group called SO10. Or let me take another group called SU5, randomly. SU5, these are minimal, in some sense, grand unified theory, especially SU5. And there you have a Higgs which is a joint. A joint representation of SU5 would have how many fields? Forgive me for these extra minutes, but let's get a flavor immediately, 24. So SU5 will break down to what? It has to break down to the standard model. And then that means that, and the standard model has how many generators? See, this is sort of trying to see how quick you are, not on your feet, on your...
What?
The standard model is scalar. Standard model is everything.
Good.
SU3 cross SU2 cross U1.
Good.
12.
I said.
Oh my God. You said?
Yeah.
Oh, I'm sorry.
Doesn't matter.
Good. Sorry. Okay. He was faster. Okay. Second. Okay, so there are 12 of them. So you see, I got 24 minus 12, right? So now I know how many Goldstone bosons I have. But there were 24, so it cannot be that I have one, you know, there'll be something else. Out of 24 minus 12 is 12, not just 1. So in a general situation, remember, there is a mass. You can know.
When you say that they are not Higgs particles, you mean that they don't have this mass term? And what do you mean when you say that they are not Higgs? The remaining particles are not Higgs.
The remaining particles are not Higgs, but they will not have a mass proportion. Well, so you're asking a very good question that is not trivial to understand. Answer nicely, but let me try. Of course, every particle either is massless or mass is proportional to V.
Yeah.
There is no other scale. So whatever I get out of my theory will have a similar mass to the Higgs. It won't be the Higgs. The Higgs we will call particular particle is the particle who lives, it's the guy who lives near the vacuum expectation value. You see how I defined it? It's the body of the vacuum expectation value. This is the Higgs. There may be other particles here, like a Goldstone boson. The characteristics of the Higgs is living together. So particularly for the Higgs, everything is given by 1 and the same lambda. That doesn't mean that there are no other particles whose masses will be proportional similarly. Oh, remember, however, in general there is more than one coupling constant, so this situation is a mess. So I don't know if I can answer it yet at this point. We'll have to do maybe one non-trivial example. A beautiful thing, but nobody wants to do it. I often give us SU5 homework. And I give you extra credit for that, and then it happens usually nobody does it. Then I give it at the exam. So it's better to learn earlier while you can still talk to me. But anyway. Okay, you see, you are getting a graph. I like the question you're asking. They're touching into the core of what we have to understand. I will be very happy if in the end you get a sense of what may happen. In particular, we will have to worry about Victor's question, what distinguishes the Higgs from other guys which are massive, whose mass also is proportional to V. That will be, it's very easy to distinguish it from a Goldstone boson. Goldstone boson, not only it's massless, it's particularly massless. By the way, the beauty of the Goldstone boson, which I should have said, is that it's massless to all orders of perturbation theory. That's what he proved. And that because it's not just that he got accidentally mass zero. It's really, its massless, it has to do with the physical thing that it corresponds to a flat direction. in your potential. Simply in that direction there is no resistance. So it will never become a fast, you can relax. It may, some of the last things may have been a little fast, so we'll start on Monday by recapturing the Goldstone and say a few more things. I try not to say too much, like Feynman. You can see that I like to keep on going after you in cafeteria. Give me a ear, I have more to say. But let's stop. I'm hungry too, not just you guys.